Hi everyone. So in today's video, we're going to talk about another rule that helps us to find missing sides and angles in triangles. So on Monday and Tuesday's video, we talked about a rule called the Law of Sines. And so I just want to remind you what that was and kind of look at what are the situations where we could use the Law of Sines, because today we're going to see some examples where you cannot use the Law of Sines and we're going to have to introduce a new rule instead. So the Law of Sines says that if you have a triangle with three angles, A, B, and C, and then the sides are labeled with lowercase a, b, and c, basically if you take sine of any angle and then you compare that to the side length of the side across from that angle, the ratio you get is going to be consistent. So we saw in both Monday and Tuesday's videos different kind of triangle setups where you can use the Law of Sines. So we saw that you can use the Law of Sines if you are given. And so what I mean by if you are given, so we talked about this idea of like, what information do you know, what information do you not know? And we use that language of, we talked about side, angle, and then also, I always mix up what I'm gonna say, angle, side, angle. So basically when you're doing one of these problems with Law of Sines, and then we'll see with Law of Cosines as well, you're usually given some information. You're told like angle C is this, side A is this. And depending on what pieces of information are given to you, that will influence whether you're able to use the Law of Sines or not. So we saw two different situations where you could use the Law of Sines. One of those situations is if you know an angle, and then you know a side that is between that angle and then another angle. And so this is called ASA. So why are you able to use the Law of Sines here? Well, because of how the Law of Sines is set up, basically you need to be able to write down an equation where there's only one thing you don't know in order to be able to solve it, right? So for example, in this case, you could first start by finding this third angle, because if you know two angles, you know the third angle. And then you could say sine of this angle over this angle, or over this side, is equal to sine of this angle over this side. And there would only be one piece of information that you were missing, so it would work. The other type of triangle where we saw you can use the Law of Sines is if you know, and let me make sure I say this in the right order, if you know a side, and then an angle. And so that is referred to as SSA. So why does that work? Well, because in this situation, you can say sine of this angle over this side is equal to sine of this angle over this side. And then that will allow you to find this angle. So it basically just has to do with, do you have enough information to write down equations using the Law of Sines and have the correct number of unknowns to be able to solve. So now let's see some examples where you cannot use the Law of Sines. So what about if you're given, for example, just all three sides? So this would be referred to as SSS. Or the other one that we want to look at is if you're given an angle, and then you're given a side and another side that are kind of like around that angle. And so that would be referred to as SAS. So I want to write down a couple of concrete examples of those so that we can just see exactly why it is that we cannot use the Law of Sines. So for example, let's say that you have a triangle, and let's say A, B, C, and this side has length 8, this side has length 5, and this side has length 12. So why would this not work? Well, if you were to try to use the law of sines in this case, you could start with something like this. You could say sine of A over 5 is equal to, and then you don't know any of the angles. So you could say sine of B over 12, but now you have two things that you don't know. And so you're not going to be able to find both of them with only one equation. And so basically without having any angles, you just aren't really able to take advantage of the law of sines. An example of the other one, SAS, that would be something like this. So let's say that you know that this angle is 46.5 degrees. You know that this side is 10.5, and you know that side C is 18. So why would this not work for the law of sines? Well, again, like if you tried to set up, you might start by saying sine of 46.5 degrees, since that's the one angle you do know. But then you would have to say over A, and you don't know A. And then if you try to do it with one of the other angles, well, you don't know either of the other angles. So if you wrote down this, for example, you would not be able to solve this because you have two things you don't know. So in both of these examples, the law of sines basically falls short. And so for both of these examples, so in these situations, you need to use the law of cosines. So I'm going to next introduce what that law is, and we'll kind of talk about kind of the way that I think about it and the way that I try to remember it, and then we'll look at a couple of examples. So, okay, so the law of cosines is, again, it's a relationship between the angles and sides of a triangle, but it's a little bit different than the law of sines in that it's not, so the law of sines is like the same for every side and angle, right? So the law of cosines isn't really set up like that. So I'm going to write it down. So law of cosines says that C squared, so that's referring to the side length C, is equal to A squared plus B squared minus 2 times A times B times cosine of angle C. So this might seem a little familiar. At least for me, when I look at this, I kind of immediately think, oh, it's a Pythagorean theorem. And so I think the best way to think about the law of cosines is actually to kind of compare it in your mind to the Pythagorean theorem. And so I want to first do a couple of examples, and then I'll show you why, or I'll kind of try to show you what the relationship is between the law of cosines and the Pythagorean theorem. But I don't want to get too lost in that idea right now before we get into an example. So let's start by looking at some examples. So one thing I just want to mention, so most people will kind of remember the law of cosines in this form, but depending on what sides and what angles you know, you might not want to use it in exactly this form. So basically, the same exact relationship exists no matter what side and angle you're kind of focusing on. So I guess what I mean by that is, in this case, notice that the only angle we're taking cosine of is angle C. But let's say for whatever reason, maybe you knew angle A and you wanted to kind of have that be the angle you were taking cosine of. So if you wanted to instead write this down kind of from the viewpoint of another angle, well, let's say we were trying to do it to have there be a cosine of A here. So the way that I like to remember this, this formula is that whatever angle you're taking cosine of, you're going to have that same the side across from that angle on the other side of the equation. So notice how here we have cosine of C and we have C squared. So if you're doing it from the perspective of angle A, then you would have cosine of A and A squared. And then everything else in the equation is just going to be the other letters that you didn't already use. So it would be B squared plus C squared minus 2 times B times C times cosine of A. Or let's say that you wanted to do it from the perspective of B. So that would be, you would have B squared and you would have cosine of B. And then what are the other letters that are left over? They're A and C. So you would have A squared plus C squared minus 2AC times cosine of B. So why are you allowed to just kind of rearrange this? Well, you could always change the letters that are labeling your triangle, right? Like these labelings of the triangle don't really have any significance. It's not like the Pythagorean theorem where C represents the hypotenuse. When we're using the law of cosines, we're usually using it in a situation where it's not a right triangle. So there's nothing really special about choosing to call different things A, B, and C. So another way that you can kind of take advantage of this equation, if you want, and you really just want to kind of use this version of it, you can always relabel your triangle so that it kind of fits with this equation. Okay, you might not really know why I'm even bringing up all these different ways of doing it, but I think once we do an example, it'll become clear. So let's jump into an example. Okay, so I want to do the same example that I introduced earlier. So let's start with this one where we have a side, an angle, and another side. So we know that this angle is 46.5 degrees. We know that this side is length 18, and maybe let me actually label this stuff first. So let's say this is C, this is B. So this is side C is going to be 18. Side B is going to equal 10.5. And that's it. That's all we know. So if you wanted to use the law of cosines in this situation, well, think about like what information we know here. We know angle A, we know side B, and we know side C. So that means that if we use this format of it, this second one we wrote down, that will be helpful for us because that will allow us to find side length A, right? Because we'll be able to fill in what B is, we'll be able to fill in what C is because we know those two. We'll be able to put in B, C, we know what angle A is, so we'll be left with just one thing. And so that's kind of the mental check that you have to do when you're doing these questions is try to think about like, what do I know and what am I trying to find? And do I have enough information to find what it is I'm trying to find? Okay, so let's jump in and use that second form of the law of cosines. So I'll write that down again. So that's right here. So A squared is equal to B squared plus C squared minus 2 times B times C times cosine of A. So in this case, that would tell us that A squared is equal to 10.5 squared plus 18 squared minus 2 times 10.5 times 18 times cosine of 46.5. So I'm going to type all this into my calculator. I didn't do this ahead of time, so let's see, 10.5 squared plus 18 squared minus 2 times 10.5 times 18 times cosine of 46.5. Okay, so I got 174. Maybe I should put approximately. I got approximately, 174.05. So now I can take the square root of both sides. I end up with A is equal to approximately, drum roll, 13.19. So I feel like for at least the way that I see it, I think the law of cosines is a little bit more complicated to write out, but if you're trying to find a side, at least, I think it's a little bit faster because you don't have to really solve anything. You can just kind of plug numbers in and type it into your calculator all at once. And by the way, so why do I, just to point this out, so when we're talking about right triangles, we're never going to have negative side lengths. So that's why I didn't say plus or minus 13.19. I just wanted to quickly mention that. Okay, so now that we have this, this other side, now we have options. If you wanted to, you could use the law of cosines again to find and you'd be using it in a slightly different form, but you could use the law of cosines again to figure out what our missing angles are. But a lot of the time, I think what people like to do is just use the law of sines. Once you've like unlocked the information that you needed the law of cosines for, then you can just jump in and use the law of sines. So maybe let me just write down what we did. So the first step is that we use the law of cosines to find side A. But now that we have side A, now we can use the law of cosines or the law of sines to find one of the angles. And then once we find one of the angles, we can find the third one using the fact that they add up to 180. So let's just say side B. Why not? Or angle B. And the reason I'm going to do it with the law of sines right now is that I want to wait until the next example to see how it goes down to find an angle using the law of cosines, just because it's a little bit different than using it to find a side. So now that we have all this, we can go back to law of sines. So we can say sine of 46.5 over 13.19 is equal to, and so we're trying to find angle B, so we would say sine of B over 10.5. And so now we can cross multiply and we end up with, or actually in this case, you don't really have to cross multiply. Because we're trying to isolate sine of B, we might as well just multiply both sides by 10.5, right? That's probably the faster way to do this. So that's sine of B is equal to 10.5 times sine of 46.5 divided by 13.19. And so in this case, and I'll explain why in a second, there's actually just going to be one possible answer. So in the last video, we did some examples where you had to do inverse sine, and then you also had to find another possible angle that it could be. We'll see that in these situations, basically because we already know what the third side is, we're kind of locked into only one possible answer. So if you type all of this into your calculator, which again, I did not do ahead of time, 10.5 times sine of 46.5 divided by 13.19, and we're taking inverse sine of that. So I got B is approximately equal to 35.27 degrees. So why, like, how can we know for sure that that is the right angle and that there's not kind of another possibility? Basically, it's because we already know the side length of side A. And so we're kind of locked into one triangle. And additionally, in that triangle, notice that the side B is equal to 10.5. That's the shortest side. And so it should be across from the shortest angle. And if we were to use that other method for finding the other angle, that angle would end up being larger than 90, right? Because we would do 180 minus 35.27. And so that would mean that just wouldn't really work out because it'd make the angle B be too big for the side that's across from it. But the way I would just think about it is once you're locked into knowing all your three sides, if you're using the law of cosines, you can generally trust that the angle that you are using, that you get from using inverse sine is going to be the correct one. You might be able to cook up an example where that's not the case, but I think in terms of what we're doing in this class, you can get really complicated with these problems, and I'm trying to simplify it just because I don't think it's the most important thing to spend a ton of time on. So I won't give you examples where you really have to worry about that. And that goes for the law of sine stuff as well, like what we're doing on Wednesday. I think I'll try to make it clear if there might be two solutions, because I just don't want that to be something that really like bogs you down. Anyway, so we found this angle, and now we want to find the last angle. So to find the last angle, we can just do 180 minus these two. So 180 minus 35.27 and minus 46.5. And so we're left with 98.23 degrees. And that's it. So key step was, again, that we had to use the law of cosines for that first step and kind of deciding which version of the law of cosines to use. And one thing that you can just kind of know as a general rule, so remember, this is a type of triangle where we had an angle, a side, and an angle, right? This was an ASA triangle. Angle, side. Or sorry, did I said ASA. I meant to say SAS. Like I said, I'm tired, but I'll do my best. So if you have a side angle and another side, then basically the angle that you're given, that's going to be the one, that's going to be like the angle that you're going to be taking cosine of. So you can kind of use that to tell you which version of the law of cosines that you want to use. But again, if you just kind of go through like, what do I have enough information to find, you'll see that that's really the only one that you actually can use. Okay, so I want to do one more example. We're going to keep this video a little bit shorter because we'll do some more examples in tomorrow's video, and we'll also do some examples of word problems in tomorrow's video as well. So the other situation where you can use the law of cosines is if you know all three sides, but you don't know any angles. And personally, there's something that I find kind of like cool about that. Like, I don't know, it just feels kind of magical that you can just like find the, oops, that's not B. Actually, I'm going to label this a little differently than I did earlier. So to be consistent with what's in the book. But yeah, I think it's like a little magical that you can, without knowing any angles, figure out what all the angles are just by using this rule. And then A is going to be equal to 5. Okay, so in the case where you know all three sides, but you don't know any angles, you can actually use any of these three versions that we wrote down. It doesn't really matter because it's like the situation here is pretty symmetric, right? There's nothing that we know more information about than anything else. And so what's going to happen is we're going to use the law of cosines to find an angle. And then once we have that angle, then we can move forward to use either the law of cosines again or the law of sines to find the other information. So maybe let's do it from, let's start by trying to find angle C. So we're going to focus on that. So if we're trying to find angle C, that means that we're going to want to use the version that says C squared is equal to A squared plus B squared minus 2 times A times B times cosine of C. So let's start putting in some information. So we know that C is 12. So we have 12 squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 times cosine of C. So we have 144 is equal to 25 plus 64 minus, so 2 times 5 is 10, so minus 80 times cosine of C. So where are we going from here? I mean, we want to isolate cosine of C, basically. So this is going to be similar with the law of sines, like the example that we did, like looking at this example. When we were trying to find an angle, we started by isolating sine of that angle, because then we could use inverse trig. So similarly, we want to isolate cosine of C. So how are we going to do that? Well, be really careful. One thing that I see students do that is a big mistake to make is that you cannot combine these numbers. Why can't you combine them? Well, if you were able to combine them, then the equation would have looked like this. But it doesn't look like that, right? So make sure that you kind of keep that stuff separate. This is the coefficient of cosine. These two numbers are separate and they're going to get added up separately. So what we can do is subtract all of those numbers over here. So we have, so 25 plus 64 is 89. So we're going to have 144 minus 89 is equal to negative 80 times cosine of C. And so 144 minus 89 is 55. And so now we can divide both sides by negative 80. So we get negative 55 over 80 is equal to cosine of C. And I think that can be reduced, but we don't really need to worry about that. So you might look at this and say, whoa, wait, is something wrong? It's negative, but it's actually okay. So let's look back at what this picture looks like. So C is the biggest side, and so C is going to be the biggest angle. And just based on like the rough sketch I made, it looks like C is going to be bigger than 90 degrees. And so if you think about it, if you have an angle that is bigger than 90 degrees, so if you go to an angle like this, let's say this is angle C, the x coordinate of that point is going to be negative, right? Just because of the quadrant it's in. So there's nothing wrong with cosine of an angle being negative within the context of a triangle. It just means that that angle is bigger than 90. So don't worry if you see that happening. What you would worry about is if you got something where it was like, say you had 80 over 55 is equal to cosine of C. That should be a place to worry because 80 over 55 is bigger than 1. But as long as the number that you have here is between negative 1 and 1, you're good. So now we want to take inverse cosine of that number. And I'll talk in a moment about why it is that in this case, actually, you don't need to worry about there being another possibility. When you do inverse cosine, that's going to actually just give you your answer. So if we take inverse cosine of negative 55 over 80, we get 133.43 approximately. So now we can go and put that up here. So why is it that we can kind of like quote unquote trust inverse cosine to always give us the right answer versus inverse sine sometimes didn't? Well, if you think about it, so inverse cosine gives you angles that are between 0 and pi. And that is like the entire range of angles that could possibly be in a triangle, right? You can't have a triangle with an angle bigger than 180. And so because basically all angles from 0 to 180 are included as possibilities for cosine, you're never going to miss a possibility by using this. So that's one thing that's nice about the law of cosines is when you're trying to find an angle, you don't need to worry about this like, can I trust that this is the right answer or do I have to check this other angle business? You just don't. You can just do inverse cosine and it's guaranteed to be the right answer because inverse cosine is going to give you a different angle for every input and those angles will be anything from 0 to 180. Whereas with inverse sine, gives us angles from negative 90 to 90. So with inverse sine, if you have an angle that is actually out here, like if we were trying to find this angle actually, this angle of 133.43, if we were trying to find that with the law of sines, it wouldn't have given it to us because the law of sines only gives you angles between, or sorry, not law of sines, inverse sine. That only gives you angles up to 90 degrees. And so that's why you have to, in order to find obtuse angles, so angles bigger than 90, if you're using inverse sine, that's where things get funny. But because of how the kind of angles that you get out of inverse cosine just kind of work out better in the context of triangles is what I would say. So long story short, with law of cosines, you just don't need to worry about that other triangle possibility. Okay, so from here, now we can kind of do whatever we want. So we can use the law of sines, we can use the law of cosines again. Maybe let's just use the law of cosines again, just to get a little bit more practice. So the first thing we did was we found angle C. Now let's say we want to find angle B. So maybe I'll just use another color to mix things up here. So if we wanted to find angle B, we're now going to use the third format of this equation, where we're going to have B squared is equal to A squared plus C squared minus 2AC cosine of B. And so if we put all this in, we get 8 squared is equal to 5 squared plus 12 squared minus 2 times 5 times 12 times cosine of B. So we have 64 is equal to 25 plus 144 minus 2 times 5, so that's 10 times 12, that's 120 times cosine of B. Again, resist the urge. Don't try to combine these numbers. They don't go together. It's like if you had, 5 minus 3x. That's very different than 5 minus 3x, right? So if there's no parentheses, assume that coefficient is not connected to the other numbers. So this is going to be on the right-hand side, that's 169. So we have 64 minus 169 is equal to negative 120 times cosine of B. So on the left-hand side, we get, I'm just going to do this on a calculator because my brain isn't awake enough to figure it out. So negative 105 is equal to negative 120 cosine of B. And so we end up with negative 105 over negative 120 is equal to cosine of B. And again, you could definitely reduce that fraction. I'll just get rid of the negative signs. But we can find B by doing inverse cosine of 105 over 120. So inverse cosine of 105 divided by 120 gives us B is approximately equal to 28.96 degrees. And notice in this case, the thing we were taking inverse cosine of was positive, and that's because our angle was in quadrant 1. It was less than 90 degrees. And so now we know that this angle is approximately 28.96 degrees. And then we can find the third angle by subtracting that and then subtracting also 133.43. And we should be left with a pretty small angle. Yeah, so the last angle ends up being angle A is approximately 17.61 degrees. So yeah, so basically that's how you use the law of cosines. So we saw first an example, right, where we use the law of cosines to find a missing side. And that's when you have the setup where you have side, angle, side, and you're always kind of setting it up so that whatever the angle is, that's the angle you're taking cosine of. But that's if you are trying to find a side length. If you're trying to find an angle, then well, it kind of depends. I mean, I guess if you have side, 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 you can start with whatever angle you want. But in general, if you're trying to find an angle, you would want to, again, kind of choose that to be the angle you're taking cosine of, and then you end up using inverse cosine at the end. So the last thing I just want to quickly show you is one way that I like to think about the law of cosines. So the law of cosines is, I like to call it a generalization of the Pythagorean theorem. So what do I mean when I say generalization? So basically what I mean by that is that the Pythagorean theorem is actually kind of a special case of the law of cosines. So the law of cosines, just to remind you, let's say I'll just draw some kind of generic triangle that is not a right triangle. So if we have A, B, and C, so the law of cosines says that c squared is equal to a squared plus b squared minus 2ab times cosine of c. So it almost looks like the Pythagorean theorem, except for you have this extra thing. And so I want to think about what that extra thing really is. So the way that I like to kind of remember the law of cosines is I think about this extra part, the negative 2ab times cosine of c. I think of it as kind of this error term. It's kind of like a measurement of how far away your triangle is from being a right triangle. And so why do I say that? Well, let's look at what would happen with the law of cosines if you actually had a right triangle. So just to be clear, generally speaking, when you use the law of cosines or the law of sines, you're usually using them because you don't have a right triangle. If you have a right triangle, there's easier ways to find missing sides and angles. You can just use regular trig, you can use inverse trig. However, if for some reason you did try to use the law of cosines with a right triangle, let's see what would happen. So what happens to the law of cosines when you have a right triangle? So I'm going to draw our right triangle so that the right angle will be angle C, just as that's kind of what we're used to with the Pythagorean theorem. So let's say we have angle C, and then these are just A and B. We don't really know what those ones are. And then we have our sides. So if you try to do the law of cosines with this right triangle, you would have, so let's say we were doing it in the format that was written up here. So that c squared is equal to a squared plus b squared minus 2ab cosine of c. So we would say c squared is equal to a squared plus b squared minus 2 times a times b times cosine of 90 degrees. So what is cosine of 90 degrees? Well, if you go on the unit circle and you go to an angle of 90 degrees, the x coordinate is 0, so cosine of 90 is equal to 0. So you'd get c squared is equal to a squared plus b squared minus 2 times a times b times 0, which is just c squared is equal to a squared plus b squared, which is the Pythagorean theorem. So basically my point here is that if your triangle is a right triangle, the law of cosines is actually just the same thing as the Pythagorean theorem. And if your triangle is not a right triangle, basically you can think, again, like I said up here, you can think of this 2ab times cosine of c thing. Basically, the closer that angle C is to 90 degrees, the smaller or the closer to 0 cosine of c gets, right? Like if you were to go on the unit circle and draw an angle really close to 90, and I meant to use a different color here. So let's say you had an angle that was really close to 90, the x value of that angle is going to be really small, right? So cosine of the angle is going to be really small. And so that's why I said that this thing that I circled in yellow here is kind of like an error term. So I would say that this is you can kind of think of this as a measurement of how far off the triangle is from a right triangle. Or in other words, how far off angle C is away from being a right angle. So you don't need to understand that in order to, or think about it that way in order to use the law of cosines, but I just like to bring that up because I think, at least for me, it really helps me remember the law of cosines because I have kind of a way to fit it into my brain kind of alongside the Pythagorean theorem. All right, so that is it. So we'll do a few more examples with law of cosines tomorrow, especially in the context of some word problems. And I will see you then.